here this lecture is about 9-point stencil for 2D Laplacian. So recall last time we talked about the 5-point. When we use 5-point, we have this kind of structure. For any ij, you have 4 here, -1, left, right, and top, bottom. Okay, and it turns out if you do the local truncation error analysis, the tau is this AH, again, exact solution U minus FH, right? This U here, let me emphasize this for 17 times. U is the exact solution. Okay, and we see that this is one negative h square over 12. What was that? U x x x x plus u y y y y, right? Plus a to the 4th term. And we note that again this tau is ah times e, right? With e is error that we really care, because that's the error between the exact solution and the approximation. Okay, and so we can sort of we recall from 1D the default correction. We can basically solve for the majority, the dominating part of the error by knowing this, right? So the key question, as we talked about at the end of the last lecture, is that for the default correction, we need to figure out, well, what is this guy? Here again, U is the exact solution, right? We don't know the exact solution. What is this guy equal to when we have the negative Laplacian U is equal to F? Okay, that's easy in 1D. You just take a 2 more derivative. In 2D, this is not as straightforward. So basically what we have is that we know uxx plus uyy, right? That's known. What can you do to make that uxxxx uyyyy? So you see, well, we need to take this was what we know. We need to take double derivative with x. Then what we also, because there's a u to the 4th partial derivative of y, so we also need to take the double derivative with y. So that would get us a uxxxx plus a not so pleasant xxyy, which is not what we needed. This shows up again, plus we have the uyyyy. So we have this term, and therefore that term, and those are fine. So what do we do with these guys? That's a dilemma here, right? So what do we have? What do we know now is that this xxxx plus uyyyy, this is not equal to, if you add these two, you are basically taking Laplacian again, right? You are taking Laplacian of uxx uyy. This can be think of sort of as one little motivation for the 9-point stencil. The 9-point stencil basically is that, well, we have the 5 points. Okay, 5 points. All right, and by symmetry, we could have these 4 more points. Okay, these 4 more points. That would make 9 points. Then we have a complete square of the grid. All right, a square of the grid that surrounds the point ij. Okay, and if you think of this, if you connect the additional 4 points, basically have a rotation of the xy coordinate, right, rotated by 45 degrees. That observation, we're not going to derive the 9-point stencil. You could. So basically, the question is that what do you put in front of the nodal values, right? So you have this u I minus 1, j minus 1, right? And then you have u I minus 1, j, and then you have u I plus 1, j. Okay, and you have here is ui plus 1. So focus on the I minus 1 first. So here is I minus 1, j minus 1, and then j plus 1. Okay, then you have the ui's, ui j minus 1, ui j, ui j plus 1. Alright, and then you're going to get the ui plus 1, j minus 1, ui plus 1, j, ui plus 1, j plus 1. Those are 9 points. What coefficients you put in front of them, the method of undetermined coefficients. I guess just show you the result here and give you some intuition. So it turns out you put 20 in the middle, and -4, -4, -4, -4. For the new additional new 4 points, you put -1, -1, -1, -1, -1. Okay. So that means here is -1. I minus 1 j, here is -4. I minus 1 j plus 1 is -1. I j minus 1 is -4. I j is plus 20. I j plus 1 is -4. I plus 1 j minus 1, that's minus. And then I plus 1 j is -4. And here is minus. Alright, and this whole thing now divided by 6h squared instead of h squared. Okay, so this is basically like this is kind of like you have the 4 -1, -1, -1, -1 stencil. You have 4 copies of those, right? So that will take care of the 16 of the 20. Okay, and it also gets you the -4 for the left, right, up, bottom, and for the cross, for the rotated cross, we have -1, -1, -1, -1, and then we have 4 here. With a little bit more involved Taylor expansion, you see this AH, let's call that AH9 to denote is a matrix for which you are going to assemble as homework. The 9-point stencil matrix AH9, this times E, which is local Trochanter error, Okay, and that turns out to be negative h squared over 12, same thing, but we have x plus 2uxxyy. The rotated cross gives you the rotated, the mixed subderivative, the mixed partial derivatives, plus y. Okay, also, and then order h to the fourth. So so we see that as we did above, that's basically h over 12 a Laplacian of uxx plus uyy, right? But we know negative Laplacian u is f, so that's a negative h12 Laplacian of a negative f plus order h to the fourth. So that's nothing but h squared over 12 Laplacian of f plus order h to the fourth. So f is given, which means we can compute Laplacian of f. Okay, and then we can solve for the more dominant part of the arrow, and then put that part of the arrow back to the solution, or better yet, just solve it once. Okay, so the instead of solving UH from AH9, UH is equal to FH. We do UH star from AH9, UH star, this time is FH vector, okay, plus h squared over 12 Laplacian FH vector. Okay, that way you don't need to solve twice. And then we know by the local trapezoid analysis, we know that the tau star now is just equal to order h to the fourth. It's more accurate. Okay? That's exactly the same as a 1D case. In 1D we did a bit more carefully and showed more details, but here is basically the same. Okay, just if this is a little bit confusing, just go back to the 1D case. Once we have the matrix, we write it in terms of AH UH equal to FH. You don't really see whether the problem is 1D or 2D. Okay, so what do we do with that more dominant part of the local trapezoid arrow? If it's known, what do we do to that part is the same. Okay. One more remark here is that numerically, so the 5-point stencil is still more popular. So numerically, you can still do something to that, you know, to that dominant part of local trapezoid arrow. The HE is this 5, okay? H5E is negative h squared over 12 uxxxx plus uyyyy, okay? And said that this is not known, so not known with respect to f, but we actually can approximate it. We can approximate it. By, for example, you have your u, right? You have approximation to your u. So by basically h squared over 12 if you can compute the UH, x plus UH, y, then you can still have approximation to this dominating part, and then you can still update. Okay, so in which is you from AH5 UH, this is equal to f of h vector. You compute your UH, alright, and then you compute some tau h, like an approximation to your tau, which is, that's why we added the h for tau, which is this guy, UH x plus UH y. And then we do what we did slowly in 1D. So then you update UH by UH star, which is UH. You add AH5 inverse times this tau h. Okay, tau h. Alright, so that's the end of the 9-point stencil. And for the 9-point stencil, you're required to know the scheme. Like I ask you what is the 9-point stencil, you're supposed to be able to write it down. But I'm not going to ask you to analyze it. And the book, the accompanying webpage of the book has a code. So you can play with the code, including the code for the 5-point stencil. But for the 5-point stencil, everything is required: analysis and implementation and the scheme. Alright. So next time we'll start talking about the parabolic equation.